Thank you all for coming. My name is Eugene Koifman. I'm a software engineer on the Hive team at Hortonworks, where I primarily work on support for transactional tables. So the agenda for the talk is as follows. First, I'll give a few examples to motivate this work. Then I'll talk about the current functionality as it looks like in Hive 3. Then I'll talk about the design of the system, and if I have time, about some future plans that we have. So first of all, when I talk about transactions, I mean the standard textbook definition. It's operations with the asset properties, that is, the ones that support atomicity, consistency, isolation, and durability. So traditionally, Hive relied on the file system rename operation to achieve atomicity. So basically, an insert statement writes to a temporary folder, then at the end, it gets renamed to the final location. That works fine if your statement targets a single partition, but if you have a statement that writes to multiple partitions, that doesn't work. So if an operation fails, you may end up with partial writes that are visible to the subsequent readers. Now, a similar thing occurs with the multi-insert statement. And this is a insert as select construct that you find in most database systems. Hive extended with ability to add multiple insert clauses to a single select. So a single statement can actually write to multiple partitions or multiple tables for that matter. So again, if a partial failure occurs, some results might be visible to subsequent readers. Now, the other dimension is isolation. So it's a property that's important because you want, while some operation is in progress, you want to make sure that the results of that operation are not visible to anyone until it actually finishes. So conventionally, Hive provided a log manager with the standard read-write semantics to solve the problem. And it works fine in principle, but since by definition, whenever a writer is writing, it must block all the readers, that doesn't really fit well with the system, which runs a lot of very long-running queries. Now, the other dimension of this is changing existing data. So since Hive didn't traditionally support update to delete SQL commands, the only way to modify any existing data in an existing partition was to overwrite the entire partition. Again, that works reasonably if you have to do it infrequently, but if your data changes, let's say you need to change 1% of your data every hour or half an hour, then it becomes expensive. So basically, the goals of adding these transactional tables into Hive is to support these use cases and solve these limitations. On the surface, it might not seem like update-delete functionality and support for asset properties have much in common, but actually a lot of the underlying infrastructure there is pretty much the same. One thing that I'd like to sort of a caveat is that this is an extension of the Hive system, so it's meant to support a relatively low rate of transactions. It's by no means an OLTP system. It doesn't have things like searchless updates the way HBase, for example, would. So what does it look like from the user point of view? So as I said, there are these tables that support transactional semantics. First of all, not all tables can be marked transactional. Any table that uses a storage handler, such as Druid or HBase, or for that matter, any external table where the client can write to it directly, cannot support transactional semantics. And the reason is basically that Hive has to control how the data gets into the table in order to actually support the asset properties. Now, currently, we only support auto-commit mode, that is one statement per transaction, but a transaction can include any number of rows and any number of partitions and even any number of tables. And the two are actually not a contradiction. As I said, there is this multi-insert statement support in Hive that allows you to write from a single statement to multiple tables. From the reader point of view, the semantics are snapshot isolation, which basically means that when a reader starts, it logically locks in the state of the entire warehouse as it existed at the moment it started. And it's not affected by any changes that happen while that reader is running. So transactional tables generally divide into two categories. So one category that supports update, delete, and merge statement. And here you see the simple example how to create such a table. Basically, all it requires is setting this transaction equals true property. Some additional restrictions on these tables is that you cannot have a user-defined sort order on these tables. Currently, the storage format has to be org. The reason for that is that to support update delete, it places some additional demands on the storage layer, which are encapsulated in asset input format and asset output format interfaces. As of right now, Orc is the system that implemented it, though in principle other storage formats could. Now, if you use these tables in Hive 2, you know that bucketing was required in order to achieve performance, so as of Hive 3, bucketing is optional, which makes these tables easier to use. Also, again, some of the changes that were made in Hive 3 require you to run a major compaction on any of these transactional tables that were created in Hive 2. And that's really important because without running a major compaction, Hive 3 will not properly read them. So now, the other category of these transactional tables are insert-only tables. As the name suggests, they don't support update to delete functionality, but the advantage is that they work with any storage format, so they're more flexible. They do support the same asset semantics. An important related feature is if you have any tables that didn't start out as transactional tables, or flat tables as we call them, you can perform an alter table on them to convert them to transactional tables. This is a metadata-only operation, which means it's basically instant. It's the compactor, which is something I'll talk about later, will rewrite these tables in the background to make them conform to the asset format. But your ability to run update to delete statements on them is available as soon as the alter table finishes. The only requirement is that the table that you're converting has to satisfy the other restrictions that I outlined for the particular transactional table subtype. Now, again, if you used any of this functionality in the past, you know that there were significant trade-offs. So you could create a transactional table, which would support these extra semantics and operations, but there were a bunch of operations commonly used in Hive which simply weren't supported. So over the past year, we put in a lot of time and effort to actually bridge that gap. And so at this point, we have feature parity between the conventional flat tables and transactional tables. So there's basically no reason not to use transactional tables. And just to highlight some of them, import-export, load data, insert-override, these are kind of really important that are now supported. So now let me talk about the implementation of the system. Now, let me start with the insert-only tables. So first of all, since I'm talking about transactions, there is a component called the transaction manager. An insert operation, for example, it lets the transaction manager know to begin a transaction, which in turn allocates a transaction ID. And for every table that is being written from that transaction, another ID called the write ID is allocated, which determines the path to which the data, to which the data is actually written. So to go through a concrete example, let's say you have this simple insert-only transactional table. And let's say you've performed 3 insert operations, the second one of which failed. So if you looked at the file system, what you'd see is something that looks like this. Every write operation creates this Delta directory, and the actual data files are written inside the Delta directory. The numbers in the name of the Delta directory are these write IDs, which map to a transaction ID. So why is this useful? If you look at how the read process happens, first of all, the transaction manager maintains or keeps track of the state of every transaction that ever happened in the system. And so when the reader starts, it asks the transaction manager for the snapshot information. And so the way it's represented is a high watermark, which is basically the highest transaction ID ever allocated in the system, and a list of exceptions below it. That is, an exception is either an aborted transaction or a transaction that's still running. So basically, based on that information, a reader can look at the set of deltas in a table directory and filter out or skip any deltas that belong to an aborted transaction or the one that's still running. This, of course, generalizes to any number of partitions or any number of tables that participated in a transaction. Basically, all the data is written to these delta files, which, essentially by naming convention, are mapped to a transaction, and the commit of a transaction is one atomic operation at the very end when everything is written. Or if there was a failure, then it is marked aborted, but again, it's an atomic operation. So this is how atomicity and isolation are achieved in these transactional tables. Now, tables that support update and delete functionality require some additional infrastructure. So first of all, as you know, Hive runs on top of an append-only file system. So that means you couldn't update or delete a row in place that already exists in a file somewhere. And even if you could, that would create another problem because you no longer would have isolation of readers from writers, and you'd have to, for example, use a log manager, which might create problems for long-running queries. So the way this is solved in Hive is by augmenting or decorating every row in a table that supports update with something called a row ID. And a row ID is a struct which consists of several pieces of information. One is the write ID, which basically ties it to a transaction that created this row. Bucket ID is actually information about the writer, the physical writer that created the row. For historical reasons, it's called bucket ID. Really, it's kind of a bit-packed integer that has several bits of information. And a row ID is literally just the numbering of the rows as they were written to a particular data file. So now a quick example of an insert statement into a full CRUD transactional table. Again, it creates a Delta file just like before. In addition, now you see these row IDs in the data file. So why are they useful? Well, so a delete statement that in this example matches a single row, the delete statement would also create a Delta file, except this time it's a specially named Delta file called the delete Delta. And what it stores is a set of row IDs for the rows that matched your query. And so the reader at read time, it looks at this information, and basically whenever it finds a delete event matching some row, it simply skips this row. It never makes it into the operator pipeline. So this is how delete operation is supported. Now, an update is nothing but a combination of a delete of an existing version of the data and an insert of the new one. And so you can see that it creates two Delta files, one to contain the delete events, one to contain the insert events. Now, to add a little bit more about the read side of things. So again, as we saw before, a read operation talks to the transaction manager to get the snapshot information, based on which it figures out the set of files that are relevant to that read operation. From that point on, basically, the process is to split each data file into a number of splits for each processing task to work on. This is kind of the same as flat tables, or for that matter, any large file processing in Hadoop. It gets split into chunks. The extra bit here to support update delete is now it needs to localize the delete events to each processing task. So this is some information that needs to perform a remote read in the system. Since the delete events are basically 3 integers, they are sorted and are stored as an org file. Because of the compression, the amount of data you actually transfer over the network is minimal. This is a significant change in Hive 3 because previously even insert events in a Delta file had to be shipped across the network that could potentially saturate the network of the cluster. So after that, the reader applies all the delete events to skip the rows. And this is why asset input format is important, because it encapsulates kind of the logic that's needed to handle the delete events. So as you perform more and more of these update operations, you accumulate more and more delete events. Plus, the data in the primary file becomes kind of more porous. So that means you have to read more data off the disk. Over time, that adds performance overhead to the read operation. So to compensate for that, there is a process called Compactor. Again, to point out, if you're only performing insert operations on your tables, Compactor, they themselves don't really necessitate compaction. But I'll elaborate on that a little bit later. So a compactor is a background process that supports two modes of operation. One is a minor compaction, which basically takes some number of delta files and compresses them into a single file or fewer files. And that's important because your application logic may be such that you have to, the initial writes have to create small files, so you end up with lots of small files, which is not good for performance of Hive or Hadoop in general. So this will solve that problem, and it's a fairly lightweight process. The other mode is the major compaction, which actually rewrites the entire partition. And in the process of rewriting it, it actually physically skips the deleted rows based on the delete events. And so once major compaction is done, but before you've performed any more updates, your reads are essentially as efficient as if your entire data set was written by a single insert statement. An important property of the compactor is that it's completely asynchronous from read-write activity, so it runs completely in the background and doesn't interfere with the existing workload. And another part of it is the cleaner process. So once the old files become obsolete, the cleaner is something that ensures, well, it's like a garbage collector. It deletes all files, but it ensures that it doesn't do it until it's sure that no other reader can possibly need those files. So next, I'll talk about the merge statement, which is an important feature built on top of these tables. So if you come from a data warehousing background, you know exactly what it is. But if not, let me quickly explain why it's useful. So imagine that you have a table in your Hive warehouse that mirrors some table in an external operational data store. As the data in the operational data store changes, you need to somehow propagate that data into the Hive warehouse and keep your target table in sync. So merge statement is designed for that. It's a single statement that, so the way it works is you capture the set of changes from the operational data store into a temporary table, and then you use the merge statement, which looks like this, that allows you to tell the system how to match up the rows in this staging table and the target table, and what to do when the system finds a match. So it has several when clauses, which again indicate, so for example, you can say that when a row matches, then update the row, or you can say that delete the row when it matches. Now, this is, so this on clause is basically the reason why it's, for this to be useful, you really have to have a primary key on your target table, or on your data set, I should say. The advantage of this is that you can perform, sort of apply all the changes in the staging table in one statement, and consequently in one transaction in Hive. If you didn't have this, well, in this trivial example, you'd have to have two updates and one insert, which not only would be slower, but it wouldn't be atomic either. So how's this implemented? It's implemented as a write outer join, where the staging table is the outer side and the target table is the inner side. And so the join is used to actually find the match of the rows in the two tables, or between the rows in the two tables. From that point on, the result of the join is split into multiple streams, one for each when clause in the merge statement, and then the process is basically exactly the same as we saw before. So if you have an update, you generate two delta files. If you have an insert, you just generate one insert delta file. And this is, of course, the reason why it requires these full CRUD transactional tables. Now, one caveat here is that since it's a outer join, or since it's an outer join, you can't reorder the join. And the way it's set up, you potentially have a very large table on the inner side of the join. So this may, without anything extra, it may result in a poorly performing shuffle join. So to address that, there is an optimization that works, well, it works with any join, but in particular, it's useful for this merge statement. And so what it does is, at first, it examines the columns or the values that participate in the on clause of the source table and generates an extra predicate on top of the target table. Since only the rows that actually match the predicate could possibly survive the join, this is useful because it can filter out most of your large target table before it ever gets into the join processing. On top of that, since the storage layer is ORC that supports predicate pushdown, it can usually be pushed down into the table scan itself, and so most of the data may be filtered even before it gets lifted off the disk. So a little bit about concurrency. No two insert operations in Hive are in conflict because it doesn't enforce any invariants that cross rows. So the delta concept, the delta directory concept is sufficient to manage the concurrency for inserts. For updates, to prevent a lost update problem where two different transactions update the same row concurrently, write set tracking mechanism is used. And what that means is that every transaction basically keeps track of the set of data that it updated, and at commit time, it compares its own write set with the write sets of all other transactions that overlap with it, that have already committed. And if there is, if it finds that it updated the same data as somebody else, that transaction cannot commit. So it's by definition optimistic concurrency strategy. Now, not all operations are data operations. Some operations, such as, for example, drop partitions, are metadata operation. And so for that, a log manager is used. So the readers get the standard read logs. Writers, or not writers, but the DDL operations, some DDL operations acquire exclusive log. And so this prevents, for example, somebody from dropping a partition from under time 2. All right. From somebody dropping a partition from under an active reader. Now, how do you get visibility in what the system is doing? So there are these several show commands, which are more or less self-explanatory. A couple of things to point out. So show compactions, since, as I said, the compactor is a MapReduce job, so this will let you find out the Hadoop job ID of the job that's running it, so you can go to the Hadoop tools to get more information on it if necessary. If some query, for example, is somebody's complaining that the query is stuck, show logs may be useful to see if it's actually waiting on a log. It'll tell you what the log is waiting for, if there is some runaway transaction or something. And abort transaction is something that allows you to kill a transaction if necessary. Now, so these transactional tables, in addition to providing the sort of better defined semantics and update delete functionality, they also leave a detailed history of the changes in the system. And that's useful for other subsystems. So for example, result set caching. When a query first comes in and causes a result set to be cached, the tables that participate in that query, basically, for each table, the system asks the transaction manager for the snapshot information for that table, and that's stored together with the result set. So the next time the same query is seen, the system again talks to the transaction manager to now obtain the current snapshot for each of the participating tables, and this is what allows it to figure out if any of the tables have changed, if any update or insert operations happened on them. And if they did, then that means that this result set is no good for the current reader. And if they didn't, then it can be returned from the cache. Similarly for materialized views, there is a certain subclass of materialized views that support incremental view maintenance. So that means that instead of, when you need to recompute the result set, instead of rereading all the data, you can just reread the changes that happened since the last time the view was materialized. And again, it's relying on this metadata from the transactional system to compute these deltas and figure out what has actually changed. So that makes the refresh of the view a lot faster. Now, as I mentioned, in order to properly read these transactional tables, you have to talk to the transaction manager and understand how to deal with the delete events. Spark by itself is not able to do that, so it's not able to read these tables correctly, though there are open JIRAs and Spark communities looking at this. In the meantime, there is something called the Hive warehouse connector, and there is a link here where you can find more information about it. It will abstract all of that complexity and can be used from Spark to properly read transactional tables. So the next major component of the system is something called Streaming Ingest API. So this is a library that's part of Hive that's primarily designed to ingest a continuous stream of events into one of these transactional tables from, I don't know, let's say Kafka or Flume or some other tool. And so the library allows you to make a connection to a particular table, and sort of and essentially it's designed for micro batches of transactions. You can call commit every, I don't know, few seconds on this table. This API is optimized for write operations, so which is important because it may create files that are suboptimal for the read operations. So that means that the compactor for these tables is kind of more important, and so it needs to be configured to run more aggressively to kind of continuously rewrite these unoptimized files into well-compressed org files with proper indexes, etc. And again, to point out one addition in Hive 3, it supports dynamic partitioning, which means that you can actually make a connection to a partition table, and the library itself will figure out how to which row needs to go to which partition. This is important because oftentimes the stream in Kafka, for example, is not partitioned the same way as the Hive table is partitioned. And somewhat related to this, let me talk about some limitations. So right now, the transaction manager basically is part of the metastore process, and it persists its state to the same relational database as the metastore. So essentially, every time you call commit or perform any other operation on the transaction manager, you are making a metastore call and potentially a database operation. That's important, especially with respect to streaming ingest, because you need to be careful when you set up the streaming ingest to configure the transactions to not to happen too frequently. If you have 300 writers, each of which tries to commit every 10 rows, that will probably overwhelm the metastore. The same thing is unlikely to happen on the SQL side of things, because even to parse and compile the query, you're still talking to the metastore, so this system itself does not add additional overhead there. But for streaming ingest, you kind of need to be careful. So a few things that we're hoping to achieve in the near future. First of all, performance of the compactor. Right now, it overwrites or rewrites more data than it could, so it can be optimized to be more efficient with respect to cluster resources. Adding support for real multi-statement transactions where you can actually demarcate the transaction boundaries. Adding support for, so right now these transactional tables, they are, so at least the ones that support full CRUD are sorted on this internal primary key, the row ID. It would be useful to add support for these tables that can be sorted on the primary key, on a user-defined primary key. That will make some of these operations, especially operation like the merge statement, more efficient. A couple of other things to add. So here are a couple of links to the documentation where you can find more detail about this stuff. A link to the Jira if you want to contribute some patches or some features. And finally, I'm the one talking, but there were a number of people who spent a lot of their time and effort to make this happen, so thank you to them. And with that, that's all I have. So thank you for your time, and I'll take questions.
Yeah, I have a question about since the data is still like the Hive nature, we still, when we delete or update records, we still insert another file into there, and what's the performance impact of that?
What's the performance of an insert statement, or? No,
after we insert, of course, that's the file system getting bigger and bigger. There's more files or transactions. When we query the table, what will be the performance impact?
This is where a compactor comes in, right? I mean, as you create more and more files, it will compress a large number of files into fewer files, right? And that's true of whether it's insert or whether you're performing delete operations.
So there's as I said, there's a background process just to compress, but the data is the kind of deleted data is still left over in the files.
Well, the deleted data is left there temporarily until you run the major compaction. So yes, temporarily there is impact. It's hard to quantify it because it really depends on, like, if you run an update statement that hits every other row in your table, then, until you run major compaction, the performance overhead will be significant, right? Because you have a lot of delete events and you're reading a lot of useless data that never gets sent to the client, right?
Okay, good. Thank you. Yeah, got it.
Yeah.
Hi. One of the troubles that we ran into with ACID, beyond all the cool improvements coming up, is with Hive 2.1, when a query would die, and we would see it die in TES or in other areas, we would have the lock continue to heartbeat for hours, even days afterwards. Is that something that we ran into as a more uncommon, or is that something that's known that there's something improvements coming or a reason why we experience that?
I'm actually surprised that you're saying you've seen this in Hive 2. If you had seen this in Hive 1 something, then we had bugs around this. As far as I know, they were fixed, though.
It's mostly with LAP, and we also have Hive sidecars, which is the same but without the caching. It's like a standalone Hive server.
LLAP should not make a difference here. So
okay.
Basically, in Hive Server 2, there is a background thread that's started in order to do this heartbeating.
That's how we track it down, yeah.
Yeah, and so apparently there is an issue where maybe in some cases it's not being killed properly. You should definitely file a bug.
All right.